The motivation for the STM came actually way back at the end of the 70s, because at that time the semiconductor industry actually was coming close to the nanometer scale. But there was no instrument that could do at that time spectroscopy at such a small area. And therefore we thought that when we basically establish a tip and come very close to proximity of tunneling, then we would have an instrument that could do spectroscopic work. And from there, basically, the idea of scanning the tip, keeping this quantum phenomena, tunneling, measuring the tunneling current, and keep the tip constant and scanning over a surface, then if the lateral sort of resolution is good enough that you could actually image individual atoms. We knew from theoretical background that if you move the tip within the tunneling current, the diameter of an atom back and forth, you would change the current by a factor of 1,000, and that would give the instrument its enormous resolution. The big breakthrough with STM came when we were able to image the reconstruction, the so-called 7x7 reconstruction of silicon 111, and then it took a while that people basically could verify all these results obtained at the IBM Research Lab in Zurich. And it took about 3 to 4 years almost that it happened. And that was during a workshop in Oberlech in Austria that people could actually verify this work that has been done. And everybody at that workshop got extremely excited, and you can imagine. It was actually at this workshop that since the STM is relying on conductive surfaces, that the ideas were discussed how to circumvent that and just develop an instrument that could get atomic resolution on non-conductive surfaces. Gerd Binnig actually came with the idea to measure forces, interactive forces, between the tip and the sample surface. And maybe that could be done with introducing a cantilever with an integrated tip. And we took it actually from there and designed and developed first AFM based on the latest development of the STM. And it was a very compact device that the deviation of this cantilever that was measured by an STM. Basically there are a few modes that AFM can measure interactive forces, and that is you have van der Waals interaction, you have repulsive and attractive forces, and you have a conglomerate of forces acting on the tip. And basically nowadays AFM is capable of using even or showing even interaction on a chemical base. So you can interact with chemical forces with the AFM. The hardest thing at that time to make it work was obviously establishing the tunneling tip behind that cantilever, because the first cantilever I made the first cantilever out of a gold foil, a very, very thin gold foil, about a few micrometer thick, and crashed a diamond stylus used by a record player, and just glued fragments of this on as a tip, and that was the first cantilever. And then, of course, moving both of it close to the surface, and then keeping the force constant, and then scanning in X and Y. Yeah, the first time it was really working was that we showed five lines following the topography of graphite, but not on the atomic scale. Not on the atomic scale. That means we had a lateral resolution of about 20 angstroms, and a perpendicular resolution of about 1 angstrom. So we knew actually that we were on a good way, but still, in the first publication, that was not really atomic resolution, and for that sake, one of the reviewers also mentioned that, that we could not basically call it atomic force microscope because we couldn't show atomic resolution with that first microscope. But presumably they didn't dare to turn it down, because they have done so actually with the STM, and so it was published. The STM was turned down basically when we showed the exponential behavior of the tunnel current. And one of the reviewers mentioned, yeah, well, tunneling. We know about tunneling for a long time, so that should not be published. And another reviewer said, well, this is a genius sort of instrument, but it should probably not be published in a physics journal. And they left it to the editor-in-chief, and that editor said no and turned it down. And so we published it in the Applied Physics Letters. This is actually a replica of the first AFM, and the original is in an exhibition in the Science Museum in London called The Making of the New World. Right in the background of it was the Apollo capsule of one of the moon mission, and basically what I sometimes say is that the capsule, this Apollo capsule, is in good company, because the AFM has been on Mars and on that recent mission, Rosetta mission of the European Space Agency. It works obviously at any temperature, in any environment, and that opened up all these different fields, Yeah, we were very pleased to see that, and it was just these 5 lines which we then actually published, Very pleased.